Okay, and then we will finish with the introduction to this Bash and Python scripting that I mentioned. Okay, so just to start, VASP courses, course, yes, the class of today. So, okay, now I'll share also my screen. Desktop to share. Okay, so now you should see the slide, Mariam. If not, let me know.
Yeah.
Okay, cool. So yeah, okay. So today is the second class, as we already mentioned, and what we will do today. I mean, here is the updated schedule that I put. Okay, so let me explain a bit better. So now that we have some exercise that we did the previous time, so this answer one, every new lecture will be about. We will start with a very short mention of the exercises we did, mainly just to point out important parameters or important like property that we calculated. Then today we will go through the theory of the Anson 2. I will basically just introduce the exercises you need to do as Anson 2, plus some of the theory, but not all the theory. So one of the slides of VASP will be up to you. And then I will finish with some instruction for the Python and Bash project. Okay. Then tomorrow morning we meet, well, here for the E3 and then like in Zoom for you, Mario, for doing the tutorial. So we'll be as this Tuesday. We just meet here with the computer. And if you have any question about Anson 2 or Python Bash project we discuss tomorrow, then you take your time till Thursday, and then on Thursday, we start again with the usual things. So correction of the Anson 2 exercises. We check together Python Bash project to see how like you evolve, if you manage or not. And then we move to the Anson 3 theory, okay? So that was all for, let's say, the introduction. This is a standard slide as the other time. So as always, on OneDrive, you have everything. On the VASP manual, you can see all the tags. And then what we will do today is the correction of the exercises of the Anson 1. Then we will check lecture 2 and instruction for Anson 2. And then, as I said, instruction for Python Bash project. I will mainly talk about this key point meshing today. This is one of the slides that is dedicated to Anson 2. I will not go through the slides over the pseudo potential because you get a lot of theory that I don't think it's really needed. So you can go through that for you if you want, but it's a degree of theory that I don't think all of you will need, and probably none of you will need. And then here there are the exercises that you need to do. And the other thing that I found, because I forgot, is these personal notes. So basically, like here, I'll show them now. I just realized, because I had forgotten about that, that in the past, when I was attending the very same courses you are doing now, from Nuria, so from the boss, I took some notes. So basically, you see 2017, because when I was a young PhD student. So here there are exactly like the 4 lessons as I'm doing, but it's just with the note of a student of few like years ago. So you may also have a look on that. If there are some mistakes, it's because at that time I was not that. I mean, I didn't know much about the things. Let's say just small mistakes, but I think it's interesting because it's really like. I mean, I put everything that at that point I think it was needed for me because I was exactly in your same situation. So it may be interesting. Okay, so that's done. Then we come back to the slide. So we can actually start. So as I said, correction. So it's not that we are really going to correct anything. I just want to kind of go through some of the exercises and to see what is going to happen, okay? So what I'm going to do now, I'm going to enter my tecla. So just to show you what is happening. So the first important things, or let's say the first yeah, like evidence that I want to point out is that in the Anson one that you did, you may have asked yourself why you are doing like 3, well, actually 4 exercises about oxygen. And the reason why you are doing that is as simple as checking the energy that you are getting. So if you check, let's say, all the system with oxygen, so we can do like, okay, so this one, this one, and then the 3, and then also the 4, okay. And then you enter the folder and you print the last energy. I have a command to do that I call sigma, but that is like grep energy space W outcard. So if you do that and you also add in front of the CD, you are also printing the name. Okay, I don't get anything because I'm not. Well, I don't get anything. Okay, am I entering?
Sorry, the sigma means?
No, yeah. Ah, okay, yeah, because I'm actually I'm not entering the one with the solution. So it was very easy. Okay, good. So now, okay. So here, here, okay, let's see how many atoms you had because I also forgot about that. So again, I had another script to do that, another like stupid thing that is just like printing the number of atoms that you have. So you see that in this case, you have one atoms, two atoms, okay? So you have the, you already see that like here, you have an energy of minus 0.16 electron volt. When you put the spin, you go to minus 1.59, okay? So that means that you are changing completely your electronic structures. And usually when you go down in energy, means that your new system is more stable than the previous one. So that basically tell you that when you're using oxygen, you should include spin. And that is something that we would expect also from, at least when the oxygen is alone, from the experimental, let's say, from experiments, let's say. And then you see another thing. Here, this system is exactly the previous equal as the previous one. The only thing is that you are breaking the symmetry. So what does it mean that you are breaking the symmetry? It means that if you get the vectors of all the cells, you see that here you have 8, 8, 8, here you have 8, 8, 8, here you have 7, 7.58. So that means that like for these two systems, your cell is symmetric, so it's just exactly a square box. While in this case, what you have is a more distorted box with one side that is 7 angstrom, the other one 7.5, the other one 8. So that means that in this system, you're breaking the symmetry. And in many cases, or whenever, let's say, you get to results that are not that physical, you should always break the symmetry. Because the problem can be intrinsic to VASP, in the sense that VASP is applying mathematical tools, like basically like just multiplication, well, products or diagonalization of matrices. And so the problem is that if you're giving if you are giving VASP input that are too symmetric, like sometimes VASP just make mistakes due to the algorithm that is using, okay? So just by breaking the symmetry, you go to the lower value. So basically you go to see that this is the better one, okay?
You have broken the symmetry, introducing different parameters on the input section, right?
Exactly. Yeah. Just changing the poster because you change. So what you do, you change the box of your periodic cell. So you are changing all, like the system is not anymore symmetric. So before the problem is that you were putting the oxygen in the middle of the square box. Now the oxygen is not anymore in the middle of the square box because now you have an asymmetric one. So that's the solution, okay? And the other thing that you could have done was also to move what? Let's say in this case, you just have a single oxygen, so it would not have worked. But if you have two atoms, you can also move slightly one of them, again, to break the symmetry. And that would be the same, like for instance, if you have a CO molecule, it's the same. You know that if you put the CO molecule on the surface, absorb like that, then again, the system is very symmetric, so maybe you will not get to the lowest energy configuration. If you put carbon and oxygen a bit tilted, then it's much better because then, let's say your algorithm will start moving the CO to try to look for the minimum, and then maybe we just fell on the minimum. But if you put it very symmetric, then you will not be able to move. So maybe VASP will tell you, look, this is the lowest energy configuration, but it's not. And then you make a mistake, okay? So, and the other important things here, and the reason why you see this mistake, you can see in the, here actually, in the band energies, okay? So if we go to, again to the terminal, and now we enter like the one that is symmetric. So let's go to this one. And then we open the out card and then we look for band energies. Okay. Here you see where is the problem. Okay. So now you have you have one key point because we have a single key point. Okay. And here there are like the energy bands. So let's say like the energy levels where the electron can sit. Okay. And you have the two spin components. So this is like spin component 1, spin component 2. Okay. So as you know very well, like you can have an electron on each band, but you cannot have, let's say, two on each band in the sense that one needs to be with one spin and the other one with the second spin. So that's why you have them split. Okay, you have one here, and then 1, 1, 1, 1, 0, 0, 0, 2. And if we take now the electronic configuration of oxygen, you will see why this is giving problem. Okay. Okay, let's see if we can find. Okay, this is good enough. Okay, so so if we see here, like let's say in this case, we are just considering, well, we are actually considering the 2s and then the 2p. Okay, so like you know very well that what is expected to be in oxygen is that then since you have 4 electrons on the p orbital, then you should have like 2 electrons here and then 1, 1. But the problem here is that since the system is too symmetric, then what VASP is doing is instead splitting the second electron. So instead of having what I just showed, so 4 electrons and then 1 and 1, so basically you have like the 2s state with 2 electrons, then the first 2p orbital with 2 electrons, then 1, 1. What it's doing is splitting in 3, 1 electrons. And that cannot be because you cannot split an electron. An electron is elementary like charge. And the reason for that is just because the system is too symmetric. So VASP is not able anymore to locate the electron because they say, okay, everything is so symmetric that I'm just dividing by 3 the electron, and then of course cannot be. If you break the symmetry, so now if you go to see this one, okay, and we go and we do exactly the same. So band energies. Yeah. Now you see that this issue is not anymore. So you see that we have 4 electrons with 1 spin component and just 2 with the second spin component. So the first 2p state now has 2 electrons, this one and this one, while then is 0, 0. Okay. So what is happening is simply that we finally, by breaking the symmetry, we go back to this. That is what we would expect from theory and experiment. Okay, so that's what breaking the symmetry or having a lowest energy means, that you are mimicking or reproducing the system properly. Okay, before it was just an artifact, it was not just a good simulation, let's say.
Sorry to interrupt, but the 1s orbital is not represented there.
No, but why is not represented?
Because it's gonna be always filled.
Because it's an inner shell. So remember that like what we do with VASP, okay, is just we are just properly accounting for the electrons in the valence shell. Okay. So the pseudo potential that we are giving here, just consider the 2 levels. Okay, because the 1 level is the inner. So for the inner shell, we just say, okay, we have the pseudo potential there and we leave it there. So the reason why we are not using it, okay, and why you just have the 2 states. But it was a very good question. So now I'm done, and now let's see what else I wanted to point out. Yeah, I think, let's see that time because I don't want to take too much time with that. Yeah, I think we can go, well, now is the vibration. The vibration is nice. So the vibration is exactly what I wanted to, let's say, to point out yesterday. So that if you go to check now this one,
Sorry,
yeah, go ahead. Yes.
If the band is not occupied,
Mm-hmm.
and why it have energy?
So, because the point is that the energy state, you always have them there, okay?
Okay.
Because what is happening is that for the, let's say, for the band theory, that's the name, I think, in Kittel is explained better than what I'm just doing now, but you have certain levels that each electrons can occupy. And why you have more energy here? Because depending on if you polarize or not your metal, you know that the electrons can go up and up and down. You know, you have the Fermi level in the middle. So the reason why you have more energy levels is because these energy levels are there, are allowed, I mean, are possible. The problem is that your electrons didn't get like jump on that level.
Without activate.
Exactly. So that's the point.
So from this output, we can directly see that the Fermi level is, for example, -7.38. This is the
I guess so. I think so. Like to get the Fermi level, there is a easiest like thing so that we can check what.
You can also plot.
Yeah, but there is. Okay, no. Let's go to the. Ah, yes, it was good.
Band energy for the first and the second is not the same. Why happened that?
Yeah. So that this one is like is different than this one.
What? I don't know. It's the same atom, no? I think so.
Yes, I mean you have oxygen and you have different like type of electrons. Yeah, I don't know. Like I would also expect the band energies to be the same.
And the occupation, the first one is 4, and the second.
Yeah, but this is because you have the two spin component. So this is because you have this system. So you know, like the first occupation just counts for 1, 2, 3. Well, 1, 2, 3, 4, and the second 1, 2. So that makes sense. The only thing is that I would have expected like the energy level of this state to be the same, while as you pointed out, like this value and this value is different. But then I need to check why it's like that. I think it's something related to VASP directly. You know, I will not. Yeah, I need to check it. I don't know why they're different, but the important point is that these and these are the same state. Well, not the same energies, but let's say these are like the two electrons that are paired with different speed. Okay.
Maybe it's the data error in the designer or the developers.
May also be. So now, what I wanted to show now, you can take the Fermi energy from the outside. No, because it depends. It depends on the it depends. You try already? Okay, so if you try, no, it's not this one. Well, let's try.
No, maybe the solo Fermi. Yeah.
No, it's but it's also okay. Basically, like the corresponding is this one.
Yeah.
Yeah. So it's what you say, Santiago. It's -7.32. That is
Here.
like just slightly above this. Well, actually, slightly above this. Yeah. Exactly. Yeah. Okay. Good. Yes. Yeah, because this is the highest value.
And when you put a grip, you don't need to do the intercalation.
I mean, it depends. Like you can do it. You will not change. Like like this, you know, like the brackets are just very important if you want to use variables. So for instance, if you want to, I mean, now it doesn't make sense, but let's say if you're doing a script and you want to do something like that, then if you do like this, well, that still works. No, I mean, then it's not this case, but there is a case. I think this is the case. Depending on, I mean, in some cases the brackets are needed, in some cases not, but when you have just one string, they are not needed. So like to put brackets or no bracket doesn't make any difference. Okay. In general, like, you know, this time I think that what I used to keep as a rule is that when like it's always better to put brackets. So if you put brackets, you are not making mistakes. If you don't, it may happen that it just doesn't. Okay, now I understand why. Of course, like you need bracket mainly when you also want to account for space. Okay. So for instance, like if now I put two space, it doesn't take because there is just one space. So it's just for that. I mean, it also to account for some spaces that you have. Okay.
The last class.
Excellent. Now we go to the vibration because here is the one that is that we were talking about yesterday. You know? So this is the vibration that you can see on like CO molecules. Okay. So the experimental value is more than 2000. It's around 2100. and we could also calculate that. And this is the CO stretching. Okay, so here we have a CO. Yeah.
So what does this value mean?
This is the vibrational frequencies of your CO molecules. Okay,
Vibration.
vibration.
Okay.
So the frequency.
Oh, okay.
So every like molecule has some vibrations that vibrate. And in this case, the carbon, well, the CO, what they have is that there is a stretch between the carbon and the oxygen. So they are moving up and down, up and down, up and down. And these have related frequencies, that is this one, around 2,800. Actually, the experimental value is slightly different due to the intrinsic like mistakes that we have in VASP. But still, like, it's very, very comparable, okay?
And F part I.
Yeah, these are the imaginary frequencies.
Yeah, and this, how to say that?
This is the imaginary
Yeah,
frequency.
yeah.
So these are like, these became important when you need to define a transition state.
Yeah.
Or you want to see if you're in a saddle point, but it's not something that we will discuss in the answer because it's not something that you use every time in the FT. It's just very, very specific. Okay, good. I think, yeah, and then the other things that you have, I think we have already seen the other day was the water molecule. We can just check it again just to see that like what a molecular dynamic is. So now, since I want to open the things with Python for VASP, I need to like mount Tekla home locally. So like that, I mount it local Tekla home, then I zoom in. Okay, so now what? Oh, let's do a bit more. Okay, so now if I enter the folder that is in this case, yeah, 00 and so on one solution. Okay, and here we want to see how like our ab initio molecular dynamics about the water went. So this is our water molecules. Okay, then we can multiply because remember it's periodic. Okay, so I mean this molecular dynamics doesn't make much sense because I mean you will not have like such a crystalline system and that much difference between like one water molecules and the other, and that's one of the reasons why also when you see how the ab initio molecular dynamics performing. So here you can go to molecular dynamics being one, for instance, you see that, okay, there are some vibration between like the, well, the oxygen and the hydrogen. So, you know, there are some oscillation, but you see that then they are just rotating. And why they are rotating? Because, I mean, you would expect like the hydrogen to get to the direction of the oxygen to establish some hydrogen-oxygen bonds, hydrogen bonds. But the problem is, well, in this case, is partially doing that, but they are very, very far away. And then there is too much, let's say, like the system is too periodic. So the problem is that, for instance, here you are in a good direction, and the hydrogen, like, is at least like in the same line as this oxygen, but then here you see that like this is also closer to the hydrogen. So the system is ill-defined. You will not get any meaningful result. But what I wanted to show you is these things. That is this is the energy convergence. Okay, so this is the energy of your system. Okay, these are the number of steps. So basically, this is the time. Because if you remember, the ab initio molecular dynamics is against time. So we applied 100 steps, and each step was 1 femtosecond. So this means that these are 100 femtoseconds. And here you see the evolution of the energy by time, okay? And you see that there is this kind of oscillation. So it's going up and down, up and down, up and down. But the average is more or less constant. And that is happening because if now you go to see the oxycar, okay, and then you do like grep T oxycar, you see that the temperature that we are imposing in the system is not always constant. Because, as I said the other time, like with this formalism that we have in the ab initio molecular dynamics, like for VASP, what we do is we set the temperature, and with the temperature, we kind of like push the molecules to move. But the problem is that if then the molecule push too much, then also the temperature is rising, okay? So at one point there is a parameter that you use as a feedback. So if your molecule like are going too fast, so the temperature will be much higher than the 2000 Kelvin that we set, then you cool down the system. And that's the reason why you see that much oscillation. You know, you started with around 2000, then you go down, you go to 1000, then at 1000, you realize, oh no, this is too low, it needs to be 2000, then you go up and down, up and down, up and down. And since at higher temperature, there is lowest energy, so you see that here, this is going very down, but then when it's 1000, it's going up. So instead of 5, you see 24, and so up and down, up and down, up and down. Because what you are changing is the kinetic energy of your system. And you see here actually, that here you have higher kinetic energy because the temperature is higher, and here you have lower kinetic energy because the temperature is lower, so the molecule will move slower, okay? So I think these were just the important things that I wanted like to focus on for answer one, like the other one are not that important. For the next one will be a bit more interesting, let's say. So now is already answer two, so we can go quickly through the slide that I'm going to present today, okay? So that are simply like the one that you have already seen online. So this one, I think yesterday I think I uploaded them, but otherwise I will do it today. This you can access like in online through VASP. And so what we will talk about, we will focus just on the key point mesh, okay? To clarify some of the doubt that you had like in the previous day. So yeah, like sometimes I will go fast in the sense that like there are a lot of formulas here. Then again, like I don't think it makes sense for me to explain because you need to see and see them. And also many of them are not that, I mean, you don't need to learn the formula by heart because you will never use it, because actually it's VASP that you need the formula, not you, luckily. But you just need to grasp the main concept, okay? So let's say like VASP, as we said, is getting some properties of your system like energy, doing some integral over like the key point with the weight. So we were telling yesterday, okay, what is this weight of the key point? The weight is what you put in front of like a special function, okay, to get the contribution of each of these key points on the value that you want to calculate. So let's say you want to calculate the energy. To calculate the energy, you will like make an integral between the energies that you calculate at each of the key points, and then each of these energy will have a specific like weight given by if the key point is symmetric, is not symmetric, given by the mesh, a lot of other parameters. Okay. So yeah, the idea of spatial points, and here we go to what we said yesterday. Okay, that this is what this is block theorem. So that is what I introduced last time. So you can just, as I say, like when you have like a metal or a periodic systems, what you can do, you can just try to split the wave function, or like to split from the wave function a component that is periodic, okay? Because the potential, the potential that is felt by electron is also periodic, so you can split a periodic contribution, and then from this periodic contribution, like these k are basically the key points, okay, and this lives in the Brillouin zone, okay. Yeah, again, this is what we said before that you take away. As you see here, like because these slides are mainly work done by physicists and are hardcore physics, but again, like it's not something that you will ever need, so I will not take too much time with it. Instead, this is important because this is the tool, this is what we need. So in 1976, Monkhorst and Pak developed an automatic way to generate mesh of key points for your system. Okay, and this will save your life because you will not need to take your crystalline structures, from there generate the Brillouin zone, and from the Brillouin zone say, okay, now that I have the Brillouin zone, I need to think where it makes sense to have a key point given the symmetry. No, because this package already do it for you. Okay, how they do it for you? They take into account the reciprocal lattice vector of your system, and what you give as an input is the number of key points that you would like to have in each of the direction. Okay, so the direction, for the direction we mean the direction of the reciprocal lattice vectors, because here we are talking about Brillouin zone. And just to kind of explain, okay, so for instance, if you have a two-dimensional lattice, okay, so you have reciprocal lattice vector b1 and b2, what, and let's say, and you say, look, I want to have 4 and 4 lattice vector, okay? So I want, and you set like 4 and 4 as the input parameter. Then what this package is doing is just checking, okay, is there any symmetry here? And then you say, oh yeah, there is a lot of symmetry, because like this system is the same as this one, this system is, this key point is the same as this one, this key point is the same as the one, and so on. And then also like, and so you already reduce it to this part, okay? And say, look, you wanted to include all of them, but they are actually not very needed. I mean, the only 4 needed that are the reducible one are these 4 ones. And then also within this one, you say, okay, but let's take this as a cell. And then you say, we are talking about the Brillouin zone. So this is not changing your postcard. Eh? This is just the internal like algorithm of this Morse-Code path that is fixing your key point. So what is happening is that then it's saying, okay, look, this is actually symmetric with this one. Okay, so we don't need this. And so at the end, from the 16 key points that you would have used, what this package does just goes to 3 irreducible key points. Okay, these 3 ones. And then for the weight of each key point is the rule that we said yesterday. Okay, like the K1 and K2 will account for 1/4, because there are just 4 opportunities for this point to be there. While, for instance, like the O3, like this one, will account for 8, because like 1, 2, 3, 4, 6, 7. No, sorry, 1, 2, 3, 4, 5, 6, 7, 8. So depending on how many key points you would have put and how many the package is reducing because there is symmetry, then you also need to weight the key point differently. So this, I mean, it makes sense that you should account 1 and 2 just for 1/4 and this one for 1/2, because you see that like you are now studying just these, but actually these key points is the same as key point. Well, it's not the same, but it's symmetric with that key point. Okay, again, it's not something that you do it yourself. It's just for you to understand what this package is doing. And then, yeah, like yeah, here is more or less telling you like or let's say giving an example of what the key point mesh means. So the key point mesh means that, let's say, if in this axis you have the key point, okay, and here you have the energy, okay. So depending on which key points you are considering, you will have a different energies. And it makes sense that if you have a lot of these red data points, then you will have a continuous function. So you get a better estimation of energy and electronic density of your system. But if you have just 1, 2, 3, for instance, then what we would have had was, okay, let's see if I can annotate, because then it will be easier to see. So what we would have had if we had just like 3 key points would have been something like this, a spike, okay? And for instance, if we just take these 2 key points, then you will see that we will have a completely wrong estimation of the energy, because the real function, let's say, is this one. And instead, if we take these key points and this key point, we just have a flat line. So basically our result is that. And that's the reason why I tell you density of mesh, more Fourier components for doing this summation or integral, depending on like how you're doing that, so higher accuracy, okay? But I mean, it's also logical that more points you have, longer your simulation, because I mean, if you had point here, then you don't need to calculate just over 8 key points, but then you calculate over 16 key points and so on. So it's always good to have yeah, like to find a good name of the key, good number of the key points. Okay.
So I mean, in
Yeah.
this case, because this is symmetric,
Uh-huh.
so we, although they have 1, 2, 3, 4, 5, 6, 8,
Yeah.
8 key points, we just need to, in the system, they just need to calculate the 4 of them.
Exactly. It's exactly what
So
you said. Yeah.
it will be more easily. So
Yeah. Yeah, but there's the reason why the calculation, I mean, this is just to show that this is symmetric with this one. So of course the calculation that you do with VASP is just with this 4 one.
And then also we need to know where the center, because if the center is not here, maybe
Yeah.
if the center becomes the, I mean the left part.
Yeah, but the problem is that the center is always there because the center of the drilling zone is always the gamma point. Okay,
You
so
always set the gamma point because
yeah.
it can't be changed. I know.
exactly.
Oh, okay.
Yeah, so that's the point. So you don't need to worry about the center, but as you say, like you reduce the number of key points you have depending on the symmetry you have. Okay, and then as we say, like there are two choices. One is centered on gamma, so gamma is a 0, and then like you can also center it, well, shift the center, so put the center here in the middle, the center of your mesh. I'm sorry, I'm making this example, but with this graph, but don't see this graph. Think about that. Like the mesh, you can center the mesh either on the gamma, so on that 0 here, or you can maybe center the mesh on a point here, okay? And then depending on the system. Usually, we always use gamma center, okay? So that is easy for you to imagine. Then, yeah, like the algorithm of this package, just calculate equally spaced mesh, shift the mesh if you want to do, apply the symmetry operation, and extract the reducible key point. That is what we said. So from the 16 that you wanted, you just take the 3 that are really needed. And so that means that it's speeding up a lot your calculation, okay? So that's why we want to use this part. And then calculate the proper weighting depending on the symmetry, okay? Now, we go to the smearing part, okay? The smearing part is what I was talking the other day about. So this sigma parameter is like, but why we need to define sigma or not sigma? And as we were saying, like the way that you talk about the occupancy of electrons is through the Fermi-Dirac function, okay? And this, let's say this function, as I was always saying, at temperature that is equal to 0 Kelvin, that is the one that we are assuming when we do the FT calculation, not molecular dynamics, but standard FT calculation, then we are supposed to have an abrupt transition. So basically, let's say if this is the the occupancy, and these are the energy, then what we have is the occupancy of 1 till the Fermi energy, and then that goes straight to 0. But instead, by using these mirroring parameters, what we do is we have a continuous transition. So you go down slowly, and then you continue slowly, okay? And that is, as you see, a lot of formula that I don't think I really need it, but anyway. And the way that we are doing here, because it's always easy, is through doing this mirroring through a Gaussian function, okay? So that means that like the way that your function, instead of going from 1 to 0, will go continuously from 1 to 0, is done through a Gaussian that in this case is just an error function, okay? And the error function is is given by a Gaussian, you know. So if you type error function, for the one of you that don't know like the formula, yeah, the error function is a special function that that is given by this formula. So you see here that you have like inside a Gaussian, and the way it is exactly what is happening. I mean, you just need to revert it, okay? So you need to think that here you have occupancy of 1, okay? Now the energies are going up like that. And then what is happening is that in the standard approach at 0 temperature, this should be like that. You should have a step. And instead, what we are doing like that. And so, for instance, if, now I need to go back to annotate, if we take, for instance, let's say, if we take a sigma, let's say that this is, for instance, like this red curve, let's say that was a sigma that was equal to 0.1, okay? If you put in your parameter, in your integral, a sigma that is equal to and we can change the color. A sigma that is equal to like not 0.1 but equal to 2, then what is happening is that you will have something like that, you know, that your transition will be, I mean, now is not really a proper one, but will be way more softer, okay? So here you see, and if you have sigma that is equal to 0.01, instead your transition will be closer to the real one, okay? So that's the reason why then on the energy, you always see energy for sigma that tend to 0. Because if sigma tend to 0, when sigma is 0, then you don't have any more continuity, so you have the step again, okay? So now, we come back to the slide.
And in the calculator, the sigma could be 0.
You can try to put sigma equal to 0 and you see what is happening. I never tried. I think that probably
Limited.
will either fail or take a lot of time. But it may also fail. But you can try. You know, it's worth a try, you know, like no idea. Okay, so yeah, extrapolation to sigma that is equal to 0 to get the energy. Okay. Okay, yeah, these things is just another like, so we are using is mirror equal to 0 to use the Gaussian smearing. You can also use other methods, but I never use them. So don't focus on this slide because you will just waste your time, okay? That you don't really need all these things. Also this one, not really needed on our side. Okay, and instead here, we go to another important concept that is another like method to get the key point, okay? So before we say that we use the Monskor-Pack method, where you decide how many key points you want in each direction, and then the algorithm is able to get to the irreducible key point. And that system, so the package that I just mentioned, is very good when you want to calculate like metal, when you want to calculate optimization, mostly of metal and adsorbate on top. If you want to have instead very good electronic calculations, so for instance, to get to the band gap, to get to the density of state, to get to the like the band structures and all these kind of things, then there is another approach that is the linear tetrahedron method. So in this case, like this algorithm, what it does, it just divides the Brillouin zone into tetrahedra, as you can see here. And then what it's doing is that it's like it's applying a function on this tetrahedra and is integrating. So basically, let's say you are just considering each of the tetrahedra at a time, and then you consider the key points that you have there, and then you interpolate, okay? Okay, yeah. So yeah, for instance, you see here, like before, well, in this case, we have more than before, but in this case, let's say probably the previous package, the Monkor's package, will get to maybe this nave, I don't see very clearly the symmetry, but like maybe get to the 6 points, and instead what this package is doing is just dividing this into tetrahedra, and then it's calculating, it's considering just this part, and then interpolating between the other things. Okay, yeah, this is telling how you interpolate.
Is it more computationally expensive than?
No, it's not more computationally expensive. I think it's, I mean, yes, some drawback and some positive aspect. I think that for sure it gives you a much more continuous, since you have an interpolation, a much more continuous evaluation of the properties on the key points. And I assume that's the case. That's the reason why you want to use it for band gap and this kind of thing. But yeah, go ahead.
If one day, if in this case, I mean, and in the box, in the postcard, I mean, the real system, not the Prism. I mean, if there I put the oxygen in the box, I mean, just like this box, if I just put atom here, and this, if in the key points, that they doing the things.
Mhm.
So if then the symmetry is not that, then it's just doing the half of them because
Yeah.
the symmetry. So maybe they just calculate this part and this part did not do because the symmetry. They may
No, I understand, but the point is that all these packages, you just use them when you have more than one key point, okay? So in the case of oxygen, you have just one key point. So like these packages don't work, because you like all these things are just to reduce the number of key points so that you can go to the lowest number. And the lowest number possible is one. So in the case of the oxygen, you already have one, so you don't apply this method. Okay, that's the reason why the key point that you were writing was basically was just one. You were writing explicitly that you wanted to have a key points for oxygen at the position 000 of the release of the carbon code. So in that case, you don't apply this method because you just have one. Okay, so there is no way to cut down the cell because you will not use this method for that case. So the problem does not apply. Okay. Okay, and then okay. Now you see. Now here we got to the drawbacks. Okay, Santiago. So the problem, and it makes sense. I mean, it's really close to what we would expect, right? Because the tetraeder can break the symmetry of the Bravais lattice, because in this case we are not forcing anymore that the center is the gamma, but you can put the center whenever you want. Then you need at least some key points. And for instance, you will see that because if you try to apply this method with just two key points, you will just say, I fail, I cannot. For that reason, because at the end you are doing an interpolation, and in order to do an interpolation, you need to have enough points, because if you have just one point, you cannot interpolate anything. And then, as it's kind of clear here, the problem is also like whenever you're interpolating, then you can also go to under or overestimate the real. So like the good, let's say in the case of like, I guess that what is happening is also that the previous package, the Moncourse package, will be probably more computationally expensive. Or let's say, if we apply that to do very nice calculation of band gap, electronic density, density of state, where we need to have very, very high parameter of cutoff and key points, then the problem is that if we have this high number of key points and we apply the Moncourse pack method, then probably that will be very low because we will still have a lot of key points. And instead, in this case, you can reduce the number of key points, so your simulation will be faster. But the problem is that you need to make sure that you have enough key points, because otherwise you will just have the wrong estimation. Okay?
And at least 4 key points are
Here they say that you need to at least 4 key points in general. Yes.
What does it mean?
It means that like you need to give as input of this tetrahedron method. I mean, not that you need to give as input this tetrahedron method. You need to explain better. So this tetrahedra, but I think, let me see, but I think actually we have it already in there.
And this is too much abstract.
No, but let's go, because I think if I remember properly, there is one case where we are doing that. Well, we will need to use it in the answer for next week. Let's see. Yeah, exactly. This is the fact. So just to check. Yeah. So you see, okay. So it's not what I just told you. Okay, it's different because I forgot and now I remember it. So this tetrahedron method is something that you apply on top of the Moncourse pack. So you always use the Moncourse pack to generate the mesh, and you're happy with that, okay? But if you want, I guess, to speed it up, then what you do, you use this tetrahedron method that, since it takes an interpolation, will make everything faster. But the problem is also that, I mean, you do that just because you have a hell of a lot number of people, okay? Because, for instance, I think I have also the solution, because
But sorry, the first zero, what it means? The key point and that zero?
That is depending on the way that, well, we need to go to check the key point because I don't know. But
Okay.
no, but we can do that. So let's go. Because it
I think
depends.
it's always 0.
I
This
think that the 0 may be just, no, that is telling you number, okay, number of key points, okay.
but it's not equal to 0.
Okay, no, it's just a parameter 0, 1. Yeah, I think it's just a parameter 0, 1 that is telling you that it's going to generate the key point mesh automatically, okay? So I guess it's like, it's, yeah.
Would
it's
mean that you are generating by yourself.
Or probably even if you don't put 1, maybe if you don't put anything, you're still, yeah, you see, for instance, no, but this is, let's take, let's see how it was for the oxygen. So if we go to Anson 1, and
I think it's also 0.
Was also 0.
I remember, yes, but no.
So like you see, like this is the number of key points. Okay, now I understand what you do. So the reason why you have 0 there is because you don't know yourself how many key points you will use.
Okay.
Because you are generating the key points. So what you just tell it, okay, I would like to have that much key point in each direction. But then is the method that is deciding how many key points. So the reason why you put 0 is because it's just to say, look, you cannot define it. You can say this 0 as number that need to be defined. Okay? Yeah.
And if you know the number of key points, you put 1, 2, 3, or whatever.
Exactly. But in this case, if you put 1, 2, 3, then you need to put 1, 2, 3. You need to put the list of the coordinates. Yeah.
Okay.
And this is telling you that is gamma centered. These are the subdivision along the reciprocal lattice vectors.
In the part, way below.
Which one? Yeah.
In the page, this, in the Cartesian, the key points could be explained like this, or just one figure.
Yeah, I know.
And this one could be, and this could be also be right like this.
Okay, when you finish, I see. Yeah.
Like this.
Yeah, but why you want to put 4, 4, 4?
Just like key points I always use.
Yeah, but the point is that if you put the Cartesian coordinate of the key points, then you know how many key points you have. So you just need to put 4, because you know that you have 4 key points with 4 line of coordinates. So the reason why you have 4, 4, 4 is because in this case you are not defining the number of key points. You are defining like the number of subdivision of the mesh you have. So the number of key points you have. So I don't understand like.
I don't understand what does that mean. Why in this case the key points present in this form?
Because these are the coordinates, the Cartesian coordinate of your system, and
the other one is like a division of the reciprocal lattice vectors.
Maybe, but on the right first, okay. If the first non-blank character on the third line, I don't know, but I'm not even sure that this is a proper key point, because I just think that these kind of generalize like the previous case, but don't focus on that. Just focus on, because this is the important one. Okay? And then what I also wanted to see was this is mirror 5. So is mirror is that, because if you put is mirror 5 minus 5, then you go tetrahedrometron with block correction. Okay, so you can check here what it does. Yeah.
I think the number is there.
For the calculation, yeah. So it's Okay, yeah, I remember we had actually well, not a discussion about Rodrigo, but like a conversation with Rodrigo, because we never use this for optimization, but just for like to calculate. But then you see that it's telling you for the calculation of the total energy, we recommend the tetrahedron method, and then like also give a good account for electron density. The only drawback is not variational, So there's a problem with the stress tensor. And so like that is also to tell you that with VASP you need to be used to this in the sense that like somewhere they can tell you, look, don't use this for this, and then in the second line can tell you, yeah, but maybe you can use it, you know. So it's just better to get stuck with what we already do in the group because at least we are sure that it works. Okay, then so yeah, just to summarize because I made confusion. So the first one is to generate the key point mesh, and this tetrahedral method is a method that you apply on top of this mesh to interpolate between the key points. Okay, and you use this for calculation of electronic problems. Yeah, and here, yeah, it's telling you that there are also the correction by block now, so that it works better. But I mean, it's not that important. Here also nothing important. Yeah, like okay, here is an important part actually, because what is telling you is that you should also consider that you should always test the key point. So as I say, the rule of thumb is that if you have a lattice vector of 6, you should put in a non-course path 5 as the direction, because 6 multiplied by 5 gives 30, and 30 is the number you should get. But the point is that this is a rule of thumb, and that works very well for metals, but may not work that much for semiconductors. So usually, when you are not sure, what you should do is to do a like test, convergence test. So what you do, you take the same system, you just vary the number of key points you put inside, and then what you do is that if you need more key points, and you're going to get a chart, if you need more key points, then you insert more key points. Like you will get a plot of energy of your system versus the number of key points you're using. And the point is that at one point you should get to a saturation. So at one point you should see that you are just introducing the right number of key points, so that if you increase the number of key points, you are not really changing anymore much the energy. Okay? So that is exactly what is telling you in this graph. So like now, of course, is a really, I mean, now the slide is really big. But later that you see it locally, okay. Now okay, we came back, okay. These things is basically like the delta E versus the number of irreducible key points, okay? So you see, okay, let's see if I can go out, because otherwise, I mean, I don't want you to get all blind, So, and I mean, so number of irreducible key points, and this is the delta E. So this delta E is the difference of energy between probably the previous step and the second step. Let's say, is just give you an idea about the convergence of your system. So you see that, for instance, if you take this system, it doesn't make any sense to take 250, because at 50 you have exactly the same energy. Okay, so like to use 250 will just take ages to converge, but you don't have any difference in energy. Instead, the difference you see is between 1 and this 30. You see that here there is a hell of a lot of difference. So like if you take these key points, just these single key points is wrong. But if you take this one, is equally wrong in the sense that you still get meaningful results, but it will take so much time and you're actually wasting time. And that is also an important concept, I think, that you need to get during this answer. That like, it's true that the computer is running the things for you, but it's also true that the computer still consumes electricity. And electricity means money from ICQ in our case. And since many of us are also working against climate, well, for climate change, it means also that we are actually needed more coal, So, I mean, it's not that we need to think twice before running a simulation, of course not. But if we can optimize the simulation such as it needs less time, it's better, because then we have the result better, we have the result faster, we can run more things for a lot of reasons, okay? Also because, yeah, and I make another like general comment. Remember that like at least like, well, we have two main supercomputers here at ICQ. One is Tekla and the other one is Mare Nostrum. Mare Nostrum is the one that we get in the Barcelona Supercomputing Center. We have a fixed amount of power. Here in Tekla, what is happening is that there are different queues. And depending on how many simulations you run, then maybe one of your colleagues will not run them. It never happened, like usually it doesn't happen because we have a lot of computational resources. But for instance, if I am very bad in these and I always take so many key points, then maybe I will need to use so much processors myself that maybe one of you will not be able to run simulation because I'm running them slowly, you know? So that's the reason why it's good to improve the speed. Okay, then here is good because it's telling you what to do in practice. That probably is the all important slide of this. I mean, not the only important, but the main important. So energy or those calculations, yeah, here is also telling you energy. But energy means when you want to get the energy. But for the optimization, remember that we are optimizing the forces. So all the calculation that you will do today about the bulk, well, for the next time about the bulk, is optimization of forces. So you need to use this concept. So when you want to calculate density of state, then you use is near equal to -5, so this linear tetrahedron method. And then instead, if you want to do bulk optimization, then you go either with the Gaussian smearing that we have, or with methods you can also change to 1 or 2, but we never use actually in the group. We always keep is near equal to 0. Okay? And then it's telling you, and look, if you have problem, check the key points convergence because it's important. Okay? Good. So, any question?
No, but for the metal also we keep the estimate equal.
Yeah,
to
exactly.
0.
It's telling you here to use these, but we always use the Gaussian smearing, so keep this. Okay,
Okay,
don't worry
okay.
about it.
Okay.
Probably in the answer, maybe it makes you use this. So use the n equal 1, no problem, but then for your next project, we will usually use is near equal to 0.
For caution and caution metal.
Yeah, okay. So yeah, this is telling you, okay, so here we got to what we asked before. So the key point file has the structure. So this is just the title, the comment, like doesn't give anything to us. The second one is automatic generation. So basically it's telling you, look, you have the package is generating. Gamma point center. This is to tell you that you are using like this Monscore package. Mesh parameter 999. And remember, and maybe I can annotate so that we don't forget, that as I say, for at least metal, the rule of thumb is to have, let's say like 999, that means that you will have lattice vector of like,
3 or 4.
yeah, 3 or 4, exactly.
Okay.
Okay, because then you need to multiply 9 per 3 or 9 per 4, needs to give you a number that is larger or equal to 30.
But the lattice vector or the reciprocal lattice, the lattice vector?
The lattice vector,
Okay.
yeah, the lattice vector. Yeah, I mean, yeah, this, because you see, like, so the point is that, as you correctly say, so these are in reciprocal space, but between reciprocal and real, there is like, they are just 1/9, basically. Like, let's say, like, there is this kind of relationship, you know, like, well, it's proportional because you also have some parameter before. So the point is that, like, this is the general rule, just to give to this 30 number, okay? But for instance, in the computational method that we see on Monday, if you remember, like there was something different because like the threshold that I set was something like you had a mesh that, well, maybe I can just open it because then it will be clear.
1 nice means? 1 nice means?
No, 1 nice doesn't mean anything. It just means that like if this is the reciprocal like lattice vector, then in the real space, like that division will be like, it will be proportional to 1/9. Okay, because
it divided into 9.
Excellent,
Okay,
excellent, because there is you have 9. Okay.
Okay.
So yeah, what I was saying is that, for instance, if you go to what it's called, I think it was this one. Yes. So here, and so we also go a bit more to the thing. So yeah, sorry. So here, yeah, you see that now is like large enough to provide a reciprocal grid size smaller than 0.03 angstrom to the powers of -1. And this is 0.03 angstrom to the power of -1, because here we are talking about the reciprocal vector. Okay. It took me, I mean, if you're really curious, like to see why this 30 is related to this one, I can tell you by next time, because I managed one time to get why we put 0.03 here, and it's exactly the same as saying that one number multiplied by the other one gives 30, but I don't remember like now. Okay, so maybe next week I will tell you. And then, so this is done, and now, so we can clear, wait, formatting. it anymore. Where do I lose the formatting things now? Okay, well, doesn't matter. We can keep all that now. Maybe okay, I'll annotate now. Okay, now it is clear also. Yeah. Okay. And then yeah, this is just making example. Yeah. So again, like practical one. Okay. So so for molecules okay, I need to close. For molecule and atoms, one, so gamma point is enough. For surfaces, what you usually take, like typical values, never try, yeah, 999 per atom. We have this better way that I'll say just multiply that for the lattice vector, because actually like it's not much about the number of atoms. It's related, like, since the key point space is the reciprocal space, what is important are the lattice vector because they define the real space. The number of atoms is not a good parameter because in the same, depending on the lattice that you have, you can have more atoms or less atoms, depending on the system, if it is a FCC or different, okay? Yeah, so, yeah, then it's, yeah, exactly. So it's telling you that, like, for instance, if you double the cell in the real space, you see, like, so this is the double of this one, then the reciprocal space gets to 1/2, okay? And that is just because, like, reciprocal space and real space, like, are reciprocal. So basically one over the other, okay? And that's the reason why larger your system is, smaller your sample of key points, okay? So if you have a system with, let's say, as we said before, if you have lattice vector of 10 per 10, 10, 10, 10, then for the Monscore pack, 3, 3, 3, it's okay. If you have instead of 10, 30, then you may also just use the gamma point because that will be enough, okay? Depending on the size. Usually you will use system of 6 per 6 angstrom, 7 per 7, 10 per 10. So you always need to put at least 3 or 4 like subdivision of this Monscore package. So like 4, 4, 4, 5, 5, 5. Actually, the last number should be 1 because, like, when you have, well, this is for the bulk. So on the bulk, no, makes sense to have also number, but when you talk about a surface, then the last one is vacuum, so in the direction you have one, okay? But I mean, you will have all these.
I don't understand what does this mean.
Yeah, so this means, so what this means simply like, so here is the real space, okay? This is the real space.
The real space is this is real space.
Yeah, this is the real space.
Okay.
And so, yeah, and what it's telling you is that when the real space get to the double, then the reciprocal space get to the half. Okay? So, like, this is the reciprocal space of this guy. The big square is the reciprocal space of this square. Okay? So, what it means that, like, in this case, you will just need to use 2 per 4 because your real space is larger, because this lattice vector is larger, while in this case, since it's smaller, you use a 4 per 4 mesh. So what you need, the take-home message of this graph is simply that if you enlarge your lattice vectors, then you need to reduce the key point mesh. Yeah. Okay? But again, it's something that is straightforward from the things that I say, that you need to take like this number multiplied by key point mesh needs to be equal to 30, because if this number, well, if the lattice vectors then is like 30, then of course the key point will just be 1, because 1 per 30 gives 30, that is the number that we need to have.
But in this case, the wheel car will not be divided, because the key point justify 1.
Yeah, exactly. So in this case, you just block out gamma point and you don't apply, you don't use this package yet. Okay. Yeah, and then it's just telling you about the convergence test, and then we are done. So now it's 11:12. I think like last time, this time we can do even like 10 minutes break, because it's like we have enough time, and then at 11:20 we come back. Okay.
Okay.
Good. And then we also.
Just a curiosity.
Yeah.
Have you ever done a cost estimation of a typical VASP run in terms of
typical VASP run? No, but I think Rodrigo gave us the estimation about the supercomputer. No? And I think
Yeah,
like
probably sent in an email.
yeah. No, but also like lately, I think we wrote in the group we have. Oh yeah, by the way, like we have a WhatsApp group that you are not forced to join, but if you want to join, maybe useful because sometimes like we are talking about. Okay, good. We are talking about many things. I think it's because super cool.
How could I join?
And I need to have your number.
Yeah.
Either I have your number or I can send you by email like the.
I don't know my number if you want.
Yeah. But let's say like let's do it at the end of the class.
Okay.
So we don't mix the things. Yeah. So Maria wrote in the group like 1 million hours in Mare Nostrum is around 10,000 euros, and we are using. I think we have like 14 million hours per year. So I mean it's more than 100,000, no?
Yeah.
So it's still money. I mean it's not too much, but it's still some money.
Federico, que si le tengo un problema,
Yeah.
ahora que, por ejemplo, en el view function, por donde que ponemos key points para dividir entre pequeños, para hacer integración a nivel de charge density. Pero en caso de si tenemos un real estate, o sea, en la situación que solo tenemos un grande, por ejemplo, tenemos 30, un postcard de 30, 30 y 30. Entonces el key point solo necesitamos uno.
Exactly.
Y entonces, si es uno, entonces eso no hay que dividir entre tanto, va a ser así tal cual.
Sí.
Pero así está bien, me refiero que si, por ejemplo, si hacemos integración siempre tenemos que dividir pequeños para tener un...
Pero tienes que pensar, I mean, you need to think. So this is the key point.
Yeah.
Space. This is the real space.
Yeah.
Okay. So I make let's make it clearer. So that means that. Okay. Let's give some numbers. Okay. So if you have, let's say, a 10 angstrom system, that means that your key points space, your reciprocal space. No. Don't think about the mesh now. I'm talking about the Brillouin zone.
Okay.
The Brillouin zone will maybe extend till here. Okay. If you have a 30 angstrom, since the reciprocal space is 1/3 of the previous case, that means that your Brillouin zone will just extend through here. So before, your Brillouin zone was all this for the 10 angstrom, and for the 30 angstrom now is just this small one. Okay.
Oh, okay.
So that's the reason why you shouldn't worry, because like it's true that you have less key point density, but it's also true that your Brillouin zone is smaller. So since your Brillouin zone is smaller, let's say if here you were taking 3 key points, so let's put like 1 key point, 2 key point, 3 key point.
Yeah.
Okay.
Yeah.
And then you reduce it to here. Yeah, you're just taking 1 key point, but it's also true that the Brillouin zone is smaller. So the density of key points is the same.
Oh. Okay.
Clear?
Yeah.
Okay.
Thank you.
No worries. No. And now I can copy the font that I work locally.
Vamos a estudiar batch number 2.
Yeah, but I mean, we will not study it, but we will just talk about that. I mean, great. Maybe
¿Esa chica también hace simulación?
She's in a group. She's in a group in Dublin, no, in Galway, and she's in the same project of Paul. Since they are in a European project, they have to travel like you. So she will be a visiting student here as well in the future. Okay. But so like in order to save time, she's already getting the theory now.
Just if you post it, I will also tell to Mario. On Friday, I will be also on vacation, so we will do, I think, the project on Monday, Tuesday, and
There is
Wednesday.
no problem.
Nosotros como empezamos.
I mean, also because
Then,
I mean, the things is for Tuesday.
yeah, okay, but maybe if it's a long project,
No.
we could also
Ya
start on Friday.
eso, lunes, como que no.
Podríamos intentar esto. Creo que me pondría mejor con esto primero para mañana hacer el tutorial y todo eso. Y luego ya si viernes hemos acabado o lunes empezamos con lo otro, con lo de VASP.
Exacto.
Bueno.
Sí,
Pero
yo
mañana tenemos dudas de esto.
lo explicaré luego, pero la idea sería de, claro, hacer antes el tutorial exactamente y mirar también si podéis antes de mañana un poco el script, justo para ver si hay algo muy raro que no entendéis.
Vale.
Sobre todo vosotros que sois al principio de VASP. Ok.
Vale, sí, vamos hablando.
Okay.
So you are there, no Mariam, you can listen to us, you can see us, everything, good.
Yes, I can see.
So, so now we go very quickly to this answer 2. And this time we need to go through that because it's more complex than the previous time. In the sense that this time you are doing something that really makes sense. Why? Because now you will do some optimization of the bulk. So let's say in standard DFT projects, in heterogeneous catalysis, what is happening is that some experimentalists arrive, tell you, look, through XRD, I see that this strange intermetallics of, for instance, copper-13 is doing amazing things. Can you simulate it for me? And then what you do, you go to a crystallographic database, you download the CIF file, that basically means the structure. And the problem is that the structure that you get from the XRD is not optimized. I mean, or at least is not optimized for VASP. So you need to do a calculation with VASP to make sure that then that bulk will be properly optimized. It means that will be in the lowest energy configuration, because then from that bulk, you can take the surface, you can start cutting surfaces, absorbing intermediate and all these things. So what we will do in this answer is basically optimizing bulk for silicium, silica, diamond silica, then beta tin silica, like these are just different crystallographic structure of the silica, plus nickel, okay, FCC nickel. So, and on top of this optimization, you will also calculate electronic properties. So DOS stands for density of state, and band means the band structure, okay? And in order to do the red one, you need to do the previous one. Because remember that electronic structure you calculate after you have optimized the bulk. Because if your bulk is not electronically optimized, doesn't make sense to get the electronic density, because you will get, well, I mean, the electronic density you have, but I mean, like, it doesn't make sense to get the density of state, because you will define the density of state of a system that is badly defined, okay? So why we need, like in a practical approach, why we need this calculation in the future, why we will need in the future? We will need, for instance, to define what is the most stable crystal structure, and later you will have a question about that. You can say to compare, like, with experimental enthalpy of formation of some, like, experimental system. You can use in electrocatalysis to define Courbet diagrams. So Courbet diagrams are defined under, like, for bulk systems. So this, for instance, is the Purvey diagrams of copper, sulfur, and oxygen. And the way that you calculate that, basically, you calculate the energy of all these like system. So here is copper 2s. This is like crystalline copper. This is copper oxide. So you just need to, well, you have to calculate all of them, and then you apply a correction that allow you to estimate that, okay? And then why density of state and band structure is important, because then you can estimate the band gap, or as I say, the density of state. And from these two electronic parameters, you can decide or define whether a system is a metal or a semiconductor or an insulator. And again, this is something that we know very well experimentally, but things if we didn't know that, it makes sense before starting something that you check if it's an insulator or not. Because for instance, if we didn't know that nickel was a metal, and instead, and you know, like, then maybe we can use it for as an insulator because we just don't know that it's a metal. So like these two parameters are also important. So just to go very quickly on, like, there are three main things that you need to do, okay? So you can optimize the bulk. So what does it mean to optimize the bulk? To optimize the bulk just means that you change the lattice vector so that you find the lattice vector that minimize the energy of the system, okay? And there are two approaches. Later we will see an automatic approach that at the end is the one that we always use. But of course, since you know we are students and we all need to learn, we also need to find a way to optimize it manually, okay? So what does it mean to optimize it manually? That you need to change manually the lattice vector. So basically you need, instead of making just one DFT calculation, you make like 10 or 20. It's very well explained in the DFT book here, the one that I showed the first day in this page. So have a look here because it's very well explained on the procedure. And so what you do is just you get like different energy per atom versus the lattice vector that you are setting. And by taking the minimum, then you can estimate what is the lattice vector, okay? There are two approaches to do that. Like easiest and approximation 0 is to take, okay, here I forgot like a square. So this is the power of 2 here, obviously, because it is a quadratic thing. I will correct before uploading it. And then you get the minimum, just, you know, like calculating the derivative of this function, and then like, I mean, it's rather easy, you know very well how to do that. The proper way to do this is not with a quadratic fit, but is with this Birch-Moore-Nagam equation of state. And you see that it's very complex, okay? I tried when I was doing the Anson, I mean, I wrote this like equation on origin, and then I could fit, but it's a bit painful. So like, I will not tell you to use origin for that, unless you are very happy and very, you know, like you want to spend time on origin or you are very good in origin. If you are very motivated, you can consider for the one that can use Python or other like program to do it in Python. I mean, it's not something that you can do like with OpenOffice. Otherwise, just use the first one, the quadratic fit, because it's good enough for what we need to do now. Okay, and also because you will never use this manual optimization of the book again in your life, okay, because we will always use the automatic one. So practically, what you need to do, it means that you need to enter these three folders, and instead of having a standard runs file, now you will need to make a for cycle so that you don't do anymore just one calculation, but before running a calculation, you generate a postcard that has a lattice vector, for instance, of 3.5. Then you run your job. So basically like this line, you run your job. Then you print somewhere, in this case, I printed in summary.fcc, you can print where you want, like the energy, plus also you want also to print the lattice vector, because you want to have two columns. You want to have a text file, the summary.fcc, with the first column where you have the lattice vector, so 3.5, 3.6, 3.7, 3.8. And in the second column, you want to have the energy, because then you can open like, and it's really easy to do it. And I suggest you, like for the people that use like Linux, just to do it here, no need to use Excel because this is rather stable. So for instance, you can just, now, let's see. you will get something like that. Let's say 1, 2, 4. When here you will have like the lattice vector, so 2.3, 2.4, 2.5. Okay, no, and this is 2.3, 2. Okay, 2.3, 2.4, 2.5, 2.6, 2.7, and then you select them. I mean, I'm sure that you can do that, but just in case. Okay, you go here to chart. So you select it, you go to chart, scatter here. I mean, you see that this is, I mean, not a very, very good like quadratic fit, but I mean, still not too bad. And then you select the point, right click, insert trend line. The trend line will open this panel where you see like regression type. You put polynomial degree 2. You want to show the equation and you want to show the coefficient of determination. Yeah. And then you have this parameter. And then from this parameter and this parameter, you can get the proper value. So the proper value here will be 2.5. Okay. So that is what you will need to do. But of course, like you need to get these two things where here is the lattice vectors and here is the energy from VASP. So in order to do that, you will need, it's not as easy as the other time that you just needed to generate the run, but you need to generate the run and then to modify the run here in the middle to add some of this line, not all of the line, because you see that, for instance, this and this is repeated, so you don't need to repeat it, but you just need to modify this script so that you can include what you want. Okay, so here you already start scripting a bit. Then the second thing, and this is instead the nice point. Okay, here, because this is the automatic optimization of the bulk, and that will be like your life basically, in the sense that every time you need to optimize a bulk, you will do that. It's not that we will do the previous things, because this is automatic is better. So in order to do that, you will see that in the incar now you will include this tag that is called ICIF 2 or 3. And we see this is taken, so the screenshot is just like taken from the VASP manual. You see that like, depending on this parameter, you can relax different degrees of freedom. So usually you always relax like the coordinate, because now remember, like now is not anymore like the oxygen. Now we have a lot of, like we have like a crystal structure like that. So now we also need to relax the atoms so that maybe 2 atoms get closer or 2 atoms get far away. So for sure, both of them will relax the positions. And you also need to make sure that in the postcard, these positions are like free, but in the postcard of the file is already free, so you don't need to change it. But so like maybe I can just like, let's say, show that.
ECIF is in the Inca, right?
ECIF is in the Inca, but just wanted to point out another thing as well. So like, zoom in. So what I wanted to point out is that, like for sure, you have then from 2, and then let's take
Presentamos those.
what?
We presented those figures, those graphs.
No, but I mean, you don't need to present it. I will show you what you need to do for the dots. I mean, but that is the next one. Okay, let's not go too fast now. So as you see, Incar, like ECIF 3, but apart from ECIF 3 in the Incar, you also need to make sure. Well, actually here it's okay, I think. Yeah, here it's okay because you are relaxing from ECIF 3, okay? But in general, like in the future, what you will need to do is to make sure that these are selective dynamics and that you have like, I'll show you because it's easier. So in the future, what you will make sure to have, you will need to open the postcard with Python for VASP, then go to build, and then click on selective dynamics. And if you click on selective dynamics, then you see that now these TTT appear. And these are the degree of freedom. So this is X, Y, Z, the coordinate of your 2 atoms, okay? And in this case, it means that you let everything move. If, for instance, you put this, instead of this T, you put F, that means that, well, a capital F, that means that your system is free to move in X and Y. Your first atom is free to move in X and Y, but not in Z, okay? In this case, it's not important because you are forcing it to be true by putting ECIF. But if you don't put ECIF, you need to make sure that there are some true, like some T in the postcard, because otherwise your system will not move. Even if you tell, oh, optimize everything, the system after one ionic step will stop, because it will tell you I have nothing to optimize because I cannot move anything, okay? And EZIF3, like you see, like EZIF2 is not that powerful, but EZIF3 is very powerful, because EZIF3 left you optimize also the cell shape and the cell volume. So that means that apart from moving maybe this atom close by to this one and this atom close by to this one, will also like increase or reduce the cell itself. And that is very important, because what you do with the manual optimization is just that. With the manual optimization, what you do is just that you make the lattice vector larger, so also all the cell is larger, and here you just do it automatically, okay? And so here it comes to the first question. You will use more or less the same method to calculate the energy, to optimize the bulk, and then you need to define what is the most stable crystal structure of silica, okay? Because these three are different, they will have different energies. You will need to compare the energies, and the lowest one will be the most stable. So 1 of 3 will be the most stable, and then you go to experimental like values and say, look, is it right or VASP is wrong? And actually VASP should be right. The last things, okay, electronic properties. Electronic properties, as I say, like you don't do it by default, but you always need to take some previous input from previous calculation. So like for this, for the DOS and for the band structure, you will need to use the HH-card, that is basically like a file that has all the charge density or the electronic density stored from a previous calculation. So actually, like the calculation that is the initial one is the 2,1 FCC silica opt. Here you will need to put as A the A that you calculated with this manual optimization. So here with the manual optimization, you get the A. Then you go to 2,1 FCC SI opt. You put in the postcard the lattice vector that you get. So like you will see, because I should have put it. Okay, now where is the right terminal? Okay. So you will see that if you forget that and you try to run it, that will fail, because here you don't have the lattice vector. Usually here you should have a number, now you don't have, and here instead you look, insert here the value of the lattice vector from 2,1 FCC SI. So here you will need to remove this line and to add 3.53 or whatever you will get from the previous calculation, okay? And
sorry to interrupt. That optimization file that in that case the FCC has freedom on optimizing the shape. Okay, so that's why we are putting
exactly. So the point is this is, and you see here, because it's doing Ibrio -1 and NSW0, this thing is just an electronic optimization. It's not an ionic optimization.
Okay.
So here you have your system that is done. You just want to get like a proper electronic density to use it as an input for the other calculation, okay?
But in future projects, we are going to use the optimization.
Exactly, the automatic one. And actually, if you do the automatic optimization, then you don't even need to do anymore this step, okay? So actually, like, for instance, in this case,
I think we should also copy the count card to the postcard.
Yeah, exactly. Yeah, I mean, but not in this case. I mean,
no.
Wait. So in these things, you just need. Okay, forgot it. Now, yes. So in this case, I need to see two things at the same time. It's not really. Should focus on one of the screen. In this case, you just need to insert the value. Then here in this folder, you will get GAG car and also like the count car. And then, as you say, you will move the count car to this folder as a postcard. Because here you see that you don't have a postcard. Okay. So the postcard of this 2.2 will come from the 2.1 FCCSI _ opt. Okay. But I mean, like, don't worry, because everything is written here. Copy change car from use concar from as postcard. So
okay.
There is no way you can make a mistake.
And concar is, sorry?
Concar, yeah, concar should have defined. Concar is the final structure. So whenever you do a bulk optimization or optimization, postcard is your initial structure, concar is the final one, the bulk calculate. Okay?
Okay.
So now, what you will do after that is that you will need to open like the VASP run XML with Python for VASP. Now I'm going to do it in a second so you will remember. And then you check the density of state. And then checking the density of state of silica and nickel, you need to tell me, not now, but next week on Thursday, if you think that they are semiconductors or they are metal. I mean, I know that you already have the answer, but you will need to give the answer from a DFT point of view, okay? So I just show you very quickly because I already did it. So let's take, for instance, to make a simple example, okay, to see nickel. So you will open like Python for VASP space vaspron.xml, and then you will go to, well, you can see the structure if you want, that is coming here. So this is your VASP. Okay, I'll increase a bit the size. Remember that this is periodic, so it's periodic in all the like 3 dimensions. So that is a VASP. Okay, that is just a big box. And this is like, you see that it's a bit distorted because this crystal structure is distorted. Then you go to electronic. Okay, now okay, now. Okay, and you go to dose plus band. So here you see the dose, the density of state. You see symmetry because this is for spin component 1 and this is for spin component 2 because nickel is magnetic, so you're importing the magnetism. And then this is the density of state. Usually this is already kind of centered to the Fermi energy. So the Fermi energy is here at 0. Okay. Again, this is the density of state, it's not the occupation of the state. So like you have state here because the electron can be up to here. But of course they are not occupied, like the occupied electrons just steal the Fermi energy, okay? And then you can go to like show band, and here these are the bands, okay? These are the band structures. Of course, like in this case, we didn't optimize the key point sampling, so you see that these band structures are really bad because you cannot see anything. I mean, you may think, I mean, probably there is no band gap because this seems that they touch, but you know, you cannot really say. So that's the reason why, for instance, like a better one where you calculate directly the band is this one, because now here you have a completely different key point, because here the key point that you will put, you see, these are 10 key points and is defined across the brilliant zone, depending on the key point that you want to sample to have a proper band gap. So here is not using any like package, any Monscore package. And actually you see the difference because if you go now to electronic, it's always like that. There is the zoom, and now you go to dose plus band, and then now you show band. Yeah, you see that now the band are much better because now the band you see that like they are much more continuous. But why? Because this is the key points position, let's say. Here I think you're using the tetrahedron method, so you are interpolating, okay? And you see that they are interpolating rather smoothly, okay? And remember, like the density of state, I think there is a way to show this. Yeah, the density of state is just, let's say, the density of line of this band structure, okay? So whenever you have more density of state, it's because you have much more band, okay? And each band is where the electron can stay.
And the Fermi here.
The Fermi is at 0. So the Fermi is 0.
So, it has been set to 0 for Fermi. And in the Fermi.
Because this is normalized. So this, like the, I mean, not the one that VASP give you, but the output for Python for VASP is already normalized to the, is already centered in the Fermi level.
Oh, okay.
So they take the band energy that we saw before and they shift it according to the calculation of the Fermi energy that we have.
And now the electrons have been now occupied the over part of the field.
Yeah, no, now it's occupied.
I think the over part.
Yeah, but let's see it better like this. Let's see directly the density of state. No, in principle it should be occupied till here. But the problem what it is, again, like that, remember, like, okay, but maybe we can show you. So this is the density of state calculated for a system where you optimize the key points, okay, for calculating the band structure, okay? Now I show you the very same system, but where now we are optimizing the key point to calculate the density of state. And now we will see if there is any difference or if there is no difference. So now if I go to electronics, density of state, you see that it's completely different now. You see, it's completely different than before. And you see that also the bands are completely different than before. But why this is happening? Because you cannot do two simulations at the same time. I mean, either you put the key point mesh to optimize the way that you get the key point, not the key point, but like the density of state, or you optimize it to get a good band structure, but you cannot get both. So before we were optimizing the band structure, that means that the density of state that you get from that calculation is very bad. I mean, it's not the good one that you should have, okay? And instead, in this case, you get a good reproduction of the experimental system, let's say of what should be there for real, but the band structure now is much worse because you are optimizing the key points for the density of state and not for defining the band structure, okay? So like the point is the following, to make it a bit more clear. Like depending on the key point sample you take, some of the sampling will be better to calculate the band structure, some other will be better to calculate the density of state. So you always need to optimize your key points and your inker to get to what you want. So in case you want to calculate the density of state, then you calculate the density of state. In case you want to calculate the band structure, then you calculate the band structure. You just cannot do both things at the same time.
I mean, when we have just optimized the structure of, for this silica, I think. So, and the next part, we just doing something state calculation. In this case, we will give the SML equal to -5, for example, and then we doing this. But in this case, I should change the key points. For dose or for...
Exactly, you will see that the key point of the dose and the key point of the band are different between them, and they are also different between the optimization. So every time you do a different calculation, you need to have a different type of key point.
And how could we know that the dose figure is good?
Because in the inker and the key point that you will put the one that you need. So the key points for the band, we showed them before. The key points of the band are 10 key points set at a certain position. For the density of state, we are using the Monscour's path. So that is already what is telling you that one is good and the other one is not good. Because you are optimizing the key points to calculate the band structure. So that optimization of the key points with the band structure is not good for the density of state. You know?
Oh, okay.
I mean, that will be, I don't know, like to try to get a XRD spectra using a STM. I mean, you cannot, because you're using like another instrument to get something else. Okay? And yeah, here, like that. Okay, these are the two questions, the things. Here, there are just a bunch of instructions that you already got. So like, I will not repeat. These are the same as last time. This time it's easier because, I mean, I guess that some of them, you already have them with you. So now, very quickly, for the last 15 minutes, we go to the Python and Bash projects, okay? So as I say, luckily yesterday we managed, also Maria managed to install Anaconda. So that means that both Mariam and Santiago had Anaconda and can use it. And I had the age that shouldn't be there, Enrique, sorry. So for Enrique and Sishen, instead will be Bash, okay? And as I said, these are 2 and +1 main projects. And they are main projects because they are already challenging, I think. If you are very, very advanced and you see that you can also go faster, then you can also try with a third script to develop, okay? just to go closer to that. So these things that is very challenging on Python, there are also libraries for doing that. So with the library it should be easy. So you need to cut surface facets from the bulk. So I gave you as input a standardized postcard, okay, of a bulk, and you will need to generate as output postcard of the different facets. So if you have bulk of copper, well, in that case, I gave you bulk of silver, that is a standard FCC. You will need to make a script so that you get to a surface of silver 111, so you are cutting it in the direction 111. The library is doing that, so you just need to check the library, understand the library, and
We can use it.
yeah. And of course, for that one, you need to use the library because otherwise it will be too complex. And also, like, to decide how many layers you want. Okay, so like the result should be you should have a postcard ready, not to be submitted, but ready to go to the postcard that instead Enric and Sichen will do. Okay, so in your case, like the postcard, well, the surface that we usually get, either like with Python scripting or with Material Studio, is a surface that is disordered. So basically, like in the list of atoms that you have, maybe you have the first atom that is at that Z position 10, and the second atom is at that Z position 1. The problem is that you need to have it ordered because later, like whenever you do a surface calculation, you need to freeze like the 2 or 3 bulk layer and to let the 5 on top free to move, because the one on top simulate the surface relaxation and the one on the bulk instead are the solid bulk. So you need to write a script that kind of sort like the list of coordinates. So, you know, you say, okay, like this is the coordinate at Z 0.5, 0.6, 0.7, 0.9, 0.8. And then after you do that, you will need to be like, okay, good. Now I want to freeze 2 layers, and then the script automatically see which are the atoms and the coordinates that are included in the 2 bulk layer, and they just, instead of having their true, they put it to false. It's better written like in the input that I give you. I don't worry. Then second, very easy, generated the key point mesh using the Monster path. Okay, the input is the postcard, the output is the key point 5. Well, actually key point without S because that is the input for VASP. And again, not difficult because in the postcard you get the lattice vector and you just need to calculate the lattice vector from there, more or less. Well, to more than to calculate, to extract. And then you know that the key point should be like 30 divided by the lattice vector. So you just divide the 30 by the lattice vectors, and then you put these 3 numbers of the key points, key y, key x, key y, and key z, inside another part of the script that is printing you a key points file in line with the monster file. Okay, and then we go to the one that are instead like the next one. And in the case of Mariam and Santiago, if you find that this one is too complex, then move directly to this one. This one is much easier, okay? So this is calculate the surface energy, gamma, of a given facet, okay? And you can calculate in joule over square meter or electron volt over Armstrong square. Yeah, well, I mean, there is a conversion. So why you need this? Because usually the approach experimental is that you start with a bulk, then you generate a lot of crystalline facets, then you calculate the surface energy of this crystalline facet, and the crystalline facet with the lowest surface energy is the one that is expected to be the most abundant on your experimental system. Okay, so that's why we need to calculate it automatically. So VASP will give you outcome. So you let's say you do the calculation with VASP, so you will get all the energies, and that next slide that will be explained a bit better, and then you need to plug all these values inside a formula to get like the surface energy. Okay, and instead for Enric and Sichen, here much more complex, so you can try. Here as input you have 2 concar, so you have the concar of the surface and the concar of a molecule. Okay, and the output should be a postcard, so it should be a structural file when you merge surface plus molecule. So where you make sure that your molecule is on top of one of the atoms. So you start with surface alone, molecule alone, and then you make a script that combines the two postcards and give you a new postcard, a new structural file, sorry, concurrent and postcard are equivalent, they are the same shape, where you now have the molecule on top. So as I say, like,
We need to change the info.
no, because this is not VASP. These are just scripts that you do
To generate documents.
on input that you use with VASP, exactly, and then you use to generate output. But this is nothing like this is something that will let you do calculation with VASP, but it's not related. I mean, this is not something. It's something that actually, like, you don't need a supercomputer. That's why also Mariam, that doesn't yet access to a supercomputer, will do, because there's something locally that you do on your computer. Okay, so I gave you, of course, some help. So like you find in my Tekla Home 00 VASP course scripting, you will see two main folders, Bash and Python. And inside Bash, you see 3 folders, depending on the script that you are expected to do. And inside each of these folders, you have the input you need to use, the output you need to use, and also like the draft of the script. That means like your script there, and also some suggestions, some tips, tools that you should use, okay? So just to go like very, very quick on what you need to do. Okay, the division is rather clear. So Jupyter notebook with Anaconda for Santiago Mariam, for emergency chain Bash. So Bash means directly terminal, okay? Terminal of Linux, nothing more. Remember, this is very important. This is very, very, very important when you're scripting everything. Always use hashtag and comment whatever you add. Because remember that the script is not just for you. The script is for a lot of other people, perhaps in the future, maybe for new students in the future. Maybe 1 year you will not remember why you put that comment. So you need to add an explanation. So every time you add a line of comment, you should write, you put an hashtag, and then you write, okay, here I wanted to apply this command because I wanted to generate this thing, okay? Then for the surface one, you can check, and you must use, because it's much easier, because otherwise I think it will take a lot of time, this PyMargent library, okay? And also, like, since you need to calculate the surface energy with this formula, where this is the area, this is the energy of the first ionic step of your surface, so the surface before relaxation. This is the energy of your bulk structure. This is the number of unit cells that you have in your surface, and this delta E relax is basically like the difference between the energy of the surface after relaxation, so the last energy you get, minus the first energy you get in your outcome, okay? So, yeah, this is done. Now we will quickly go through the slide. Yeah, we have 4 minutes just to show you what I meant with all the things, okay? So, for instance, yeah, I think I copied them on my third line. I'll start with Santiago and Mariam because it's a bit faster. I need definitely to make this larger because otherwise I will lose my eyes at one point. Okay, so okay, okay. So they say Python. We go for instance LabGen. Okay, in LabGen you will see like the input file. So concar input, postcar output, just to show you what it means. So if you do like that, we should see all the structure. So. So this is the input, bulk silver. This is the output. This is silver 100 with 4 layers. This is silver 111 with 4 layers. This is silver 711 with, well, 4 layers, yes, 4 layers, okay? 1, 2, 3, 4. So like the script should be able to do that. And in the script, it will be nice also if you can add a parameter, I put it there, to the side of the layers.
For the void, the number of layers.
Yeah, exactly. The number of layers, the vacuum. No, to fix it, no, because that will come then from there. So that is not needed. So it just will be already very, very good if you just get like facets, and then you can tune, as you say, number of layers and vacuum, okay? And also that, but I think also the lateral extension, okay? Because you see that this is a 3x3. Well, actually, I take it better this. Yeah, so these are 3x3. You have 9 atoms. So for instance, like it can be multiplied even further, and you get to a like 4x4 atoms, 5x5. Okay, so lateral dimension, vacuum, and thicknesses. So number of layers. Okay, then
And energy holding calories.
hmm?
I'm so curious about that.
Yeah, I mean,
How to calculate the energy without mass? This kind of for the energy for each layer that they will go to.
no, but it doesn't need to calculate energies, because what it needs to, they just need to generate the input to be used to VASP. So you just need to calculate a postcard. Then this structure will need to be optimized by VASP, but it's just a structure, okay? So the other one that is much more complex, okay? Because this one, well, no, sorry, it's not the much more complex. So this, in these things, so in SlabGen, you will see that I basically didn't give any big help, because I mean, let's say I will open it directly with the Jupyter notebook, because otherwise it's getting. Okay, so by typing this, you are redirected like to this like page. I know that Santiago already know that, but mainly for you, Marion. So here you are able to run like Python command. Okay, you see all your things. Okay, now I should find a way to. Okay, yes. Okay. So you see that here, like basically, I just tell you, okay, import some of the things you may need, and then check the library. So here, like the suggestion, like 0. Okay. The things that is important for you to, I mean, also because you don't need much. I mean, this is just your bulk structure, and this is your output, but the output is not needed, because output is what you will need to generate. You see here that is like falls through and also selective, but that is not needed. Okay, or the selecting dynamic is not needed. I just forgot to remove it. Then, okay, I was stupid because I opened it inside and not outside. Then let's go here instead on the surface. I helped you a bit more. Okay, so not much more, but at least a bit more, because now here you have another notebook where this time you have. Okay, so now I'm already telling you which are the input. Okay, so you need to take, you will have a bulk structure and a surface structure. So the bulk is your bulk, and here you have different crystalline phases. Okay, in this case, to start, just make the script to work with one of these of the phases, so the 0, 1, 0. Okay, as I said, you need structural parameter because you need the area and you need the energy. So that's why I'm importing concar to get the structure and outcar to get the energy. Then here, in a very, very, very difficult way, I think you can find a better way. Like there are a bunch of commands where you can extract the lattice vectors. Okay, so in this case, you have, for instance, the lattice vector of your surface. And in this case, I already calculate the area. Okay, so here you already have the area calculated in Armstrong square, and here you have the number of atoms of your surface. So to get this number, okay, you will just need to divide this number of atoms that you have in the surface, 48, by the number of atoms that you have in the bulk. And for calculating the number of atoms that you have in the bulk, you just need to apply this and this script, but instead of taking surf struct, you take bulk structure. Okay, then the script will be exactly the same. And then to get the energy, because you also want to get the energy, because then, as I say, this will be the first energy. This is the difference between the last energy of relaxation of the surface minus the first energy, so this one, and this is the last energy of the bulk. Then you need to do this graph energy space W on Python, and you can do it like that. So in this case, what I'm doing, I'm extracting all the energies in Python. So you see the energy for the bulk, and these are the energy of all, okay, now it's very large. Okay, these are the energy of all the ionic steps. For the bulk, you just need the one, so you will need to find a way to extract this value, because remember, it's also like you need to take sigma that is equal to 0. Then you need to repeat this approach for the surface energy, and for the surface energy, you need to take the first one and the last one, because the last one, like taking the last one minus the first one, you will calculate this delta E, okay? And then you just need to apply this formula that on Python is very, 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 very simple, because it's, yeah, you see, like the way to calculate the area here is just a multiplication. And so like for Python to do any kind of multiplication is very easy, okay? So here, I think you should have, I mean, this one is rather straightforward. The other one is not. So for the other one, you will need to work a bit, okay? Now, we quickly go through the bash. So on the bash is similar in the sense that, again, like you have input and output. So for instance, let's take this. Okay, here I need, yeah, then later I will need to remove one because this actually already works. So the input is a structure, a surface that you see is disordered. Maybe I can put it a bit larger. So you see here that is 0, 25, 12, 39, 0, and you see that like you are not like relaxing any of the coordinates. And what instead you want to get is this. So you want to get, I mean, this is a pointer, okay? The last 0 point at the end is not important. You need to focus on this part. You see that here is like the beginning is the same as before. You have the selective dynamics here that before you didn't have. And then now what you have, you see that all the atoms are ordered by Z, okay? And then you have free, true, like false, true, that means like frozen, they can move, frozen, they can move, frozen, they can move. And the way that you see that is not continuous, so you have this transition by 039 and 0 here, is because this is an intermetallic. So you also need to make the script so that you don't mix the atoms, okay? Because the problem is that the way that VASP like give you the structure of an intermetallic, you put first all the atoms of a certain element and then all the atoms of a certain other element. So for instance, if on the script you just decided to order all of them together, then will be a big mess, because that you will just split the atoms. Not split the atom, but you will just like change the atom between them. So like the final system you will have will not be physical. In this case, you don't need to worry much because like the script is basically done. It's very complex. I have commented a lot of things. So whenever like you see these hashtags, it's because these are comments, okay? These are many things commented. The only problem is that, yeah, like what is happening here, exactly, like what is happening here is that the last part, these things, I mean, the ordering part is perfect, but this just fix like half of the cell, okay? So this last part doesn't say like, okay, you want 2 surface layers fixed, then I fix them. This last script just say, okay, how many layers do you have in total? 8. You just need to freeze the last 4. But instead, what I want you to have is to have the number of layers in the bulk here as an input 1. So the way that you will, okay, the way that you will run this like script will be point/order dot sh space n3 dot and where n3 will be the number of bulk layer. I think I will change this nomenclature a bit so that it's clearer because n3 is the opposite. And this will be the number of layers that you are going to fix, okay? And then, so this is more or less done. This one as well. So here, as I said before, you take as a input the postcard where you have different like lattice vector, the one that you have. Where is the mouse now? Losing my mouse. Okay, yeah. And what you want to get as an output is a key point file. Okay. The script again is more or less done because you have, yeah, again commented. Many parts are already there. The point is that they are just defined for some of the variables. So for instance, here I just get the intensity of the 3 lattice vector, but I just get the intensity of A. I don't get the intensity of B and C. So you will need to copy the same like line and also to understand what you need to change there. Okay. And then the output. So like if you want to run, for instance, this, so you run it. Okay, but now if I run it here, it will probably not work. Ah, no, it will work actually. So when you run it, it's printing some things. And then here is telling you the key point sampling for a metal are give you the three key points, like 3, and then this to be defined is because the script is not complete. Like you will need to add other things. And so for instance, you see now the script, like before in the folder, we didn't have key points alone, we just have key points output. You see that now the script generates a key point file. So we are almost done, and it's already generated in a good way, but the problem is that here we are missing one value, and the value is because you need to like complete the script. And then the very last script, that is like the difficult one, also because like the first one of Santiago and Mariam is not that commented. So you see it here, like you have some suggestion, but very general, because I mean, this is the challenging part. This is the one that like you may also not be able to do at this stage. And so what you want to do, okay. You want to start with indium palladium. You know, you have a CO molecule alone, so you have two structures of the two. And what you want to do to arrive here, so you want to move the CO on top of one of the atoms. So you need to do it in an automatic way, okay? Because otherwise, the other way will be build, text, you add a line here, you add something here, you add the coordinate here, you move, but you need to find it automatically because then you will save your time, okay? Then it's done. So like all the things, just give me some time just to check like the thing I need to change. Then like, let's say, so you can check today, like after lunch, it's okay, because I will just do it now quickly. And for that, it's okay. For the scripting part, I will also put them in OneDrive so that at least the Jupyter notebook also Mariam can access them. And yeah, that's all. I know, I mean, this last part of the scripting I know is very complex, but you also have 4 days. And you don't need to do all of them. But this script, you will have to do them probably at some point in your life. So better to start now.
And Federico, and what is the example?
What do you mean?
I mean, put a molecule from a surface, but what surface or what element?
I mean,
or in the palladium or
yeah, I mean, okay, yeah, I should have mentioned. So the example here is let's see, the example here is, well, not this one, because this one is just a molecule.
And the contract have already been calculated.
Yes.
Okay.
So here you are assuming that you already optimized the surface and the molecule alone. But what you want instead, you want to prepare a postcard where you have already, like, you have this indium palladium surface with the CO on top. So now you want to calculate the absorption of CO on this intermetallic, okay?
And the Cartesian, so it's, okay, I know.
So Cartesian, and these are the coordinates.
Okay,
so these are all the coordinates of your surface, and the last two one are the coordinates of the CO molecule that you just added. Okay. So if you do, for instance, like this, that is a nice comment. So if you take the difference between the concard and the postcard, then you see that the only difference is that you are adding CO and 1, and you're also adding 2 coordinates. These are the 2 coordinates of the zero in the second one. Okay?
Okay. And the position of the zero, is there some?
No, I mean now for this point is just to put it on top of one of the surface atoms.
No matter. Okay.
I mean, so the point is that all discrete, you may optimize them at one point, you know, like you can improve them at one point. But I mean, it's better that for now we just get to some basic script.
Okay.
And then if in 1 week you would like also to put the rotation, amazing, you know. But I mean, like, don't start too high, because like in scripting, it's always good to start with a basic script that works. And then you improve it. Because if you start already to see like the final point, then you miss the basic, and you need basic anyway. Okay. So good. And I think if you don't have questions, we are.
I have a small question. It's about, for example, because I remember when we entered Tekla that you told us that there we can consult every file.
Yeah.
But for example, if we are working in his computer, I can copy from my computer the things that he's doing outside Tekla home. I'm sorry, it's outside Tekla.
Yes. So the point is that, let's say, so if you copy some of my files on from my Tekla home to your Tekla home, then from your Tekla home, after you have my file on your Tekla home, you can move wherever you want. Okay.
But
So
we have to do it on Tekla home.
But exactly, the first transfer is just
Okay.
through Tekla.
Okay, I understand.
No, because the Tekla home is, and another important thing just for you too, because I mean, for Mariam and Santiago, that will not be a problem. You cannot work, even though like Tekla home is connected, you cannot work on the same file together. Okay, so I mean that for sure, because you cannot, I mean, you cannot modify actually each other's files, so that's good. But let's make it clear. Like for instance, if I give Enrique my password, you know, so that we can all access my Tekla home. If we both work on the same file, just one of us can work. I mean, if you try to open the same file as I have opened, then an error will appear. Like it doesn't work like a shared folder or shared file. Okay? So like all these script, I mean, for all the people, makes sense to split part, so that you take the script and like, okay, we need to solve this issue. Okay, you start thinking about that, I start thinking about that, and then after 1 day, we combine the result, okay? Because otherwise, like if you work, or you split the script, one work on a script, the other one on a second script, as you wish, but it doesn't really work. I mean, or at least I never believe in this competitive approach, so that, you know, you both work on the same script, and then the faster get the solution. I mean, it always works better to differentiate, you know, because then you work on something and then you work in parallel. And then if you work in parallel, and on scripting, it's very easy to work in parallel, because as you see, there are several sections in all of them. So, okay?
Okay, yes.
And then, I mean, like, think about that. I send you all these files, so this afternoon you will have time to check. Then tomorrow when we meet, we discuss about the answer very quickly. And then also, if you have any question about this, we can talk tomorrow, okay? Good. Nice. So I think we are done. So I can stop sharing and we say bye, Maria. Could you follow a bit? I mean, there was a lot of information today.
Yeah, it was good. Thank you very much.
If you have questions, then also write email, eh? Because I mean, I know
Thank
that
you, Chef.
unfortunately it's not as good as for us, you know, to be in the same group, but yeah.
Okay, to be honest, I get an email from our, IT system that they told me that if you are attempting to connect the software at a different location, you will need to contact the institution to request the access.
Oh. I see. Okay, so you need basically to send an email to us asking us to get to connect. No, that would be the solution.
Okay, then.
I mean, like, I guess that will be the solution, because what they are telling you is that no, wait. I'm confused now, because so the point is that you cannot connect because your own institute firewall blocked the connection. Okay. So they will need to enable this connection anyway. Then of course, like, if in order to do that, they want us to tell them, look, yeah, you can connect, then we can do that. So just send a general email. You can put me in CC. I think I should be enough. And if I'm not enough, then we put Nuria. But I mean, like, probably they just need a person from ICQ telling them, oh, yeah, she needs to connect to our supercomputer.
Okay, then.
I guess. Try with that, because
Okay.
the point is that I was talking to Martin, our lab technician, and like, the problem is for sure the firewall. Like, because I was
Okay.
so like, I know that that is the problem. Like, so that should work. And so like, just try to tell them this. You can directly put me in CC, so that, you know,
Okay,
if
sure.
they have a follow-up, then I can also intervene. And if I don't manage, then I will also put in CC Martin that can also intervene, and at one point should work. Okay?
By the way, if I come to ICQ, I will have this problem again.
No, because if you come to SAQ, you will have your own computer.
Okay, then.
If you come
Okay.
as a visiting student like Sichen, for instance, then you get your own computer in the office, and then, I mean, you don't need to connect from outside, you know? So like,
Okay.
this is mainly just for this course. So that's the point, like, it's also depending on you, how, like, you know, you can also attend it without doing the exercise. I mean, you will not die for that, you know? It's just depending on like how easy is to get this access, because let's say if then your university tell you, no, we need to write 10,000 paper, we need to do this, we need to do that, then no problem, because when you're coming here, we will solve it because you will get a computer. But since I think should be something rather straightforward, let's try what you just said, you know, that you send an email, like put him in CC, say, yeah, I need to get this connection because I'm doing a course with Federico, that is a postdoctoral researcher in the group. And if you need any more like bureaucratic things, we will also let you talk with the administrative manager of the system, that is Martin. Right?
Okay.
Okay?
Okay. Thank you very much.
Don't worry, thanks to you. Good, then I think we are done. I stop recording and we can go. Bye, Mariam.
Bye-bye.